Okay, Assalamu alaikum and good morning, right? So we started talking about multithreading in previous class, and today we're going to continue talking about that. You have seen most of the theory and the background that you need to know about multithreading. And towards the end of the class, we have shown you an example of how to create threads, okay, or multithreading program using p-threads, right? P-threads. The code was something like this, and also we have seen it running in Fedora as well, right? We have elaborations on the code, discussions, and so on. So next is to continue exploring the rest of the functions in the pthread library, okay, that you can use with C Linux. And after giving you some background about each one of these functions and how does it work, then we will demonstrate some examples using some of these functions, as well as we're gonna talk about the different type of variables a thread can deal with. We have 3 categories of variables. And then we move to Java threads. Hopefully we can cover all of that in today's class so that next week we'll talk about network programming, okay? Right. So I've seen the difference between a thread and a function. I think that was very clear. We mentioned something about threads sharing information, okay? Basically, what they share is what the process has, okay? What the process has in general, right? Threads, they do live within a process, correct? So the virtual address space of the process is shared among what? Among the threads of that process, okay? And in the virtual address space, I can define global variables. So these global variables that you define in the main thread, we agree that it's a thread. Your main process, okay, it has a thread, which is the main thread. So whatever you define in that process as a global variable is accessible by what? The threads, okay, by the threads. And there is only one copy of it at runtime. One copy of it at runtime, which means the threads, they can access this variable, right? So this is something good. However, there are some consequences. Because if we have multiple threads who run concurrently, okay, accessing a variable, then one of them might leave the variable in what? Unstable state. For example, a thread is updating the value of a global variable, okay, but not yet finished updating. And I think we have mentioned before that a simple update statement, which is incrementing by 1, saying count plus plus, involves 3 instructions, right? Loading count, right? And then adding 1 to it, and then storing it back. So an interrupt might happen in between anywhere, which will leave the variable in unstable state. So we'll have inconsistency of data. So sharing is good, excellent. Okay. However, it comes with its own problems that we need to look at and solve it, okay, by using synchronization later on. In 2 weeks' time, okay, we're going to start synchronization. So that's the last type of, or sorry, the first kind of variables. The other type of variables is what you define inside the thread, okay, inside a thread, including the main thread, right? So whatever you define within a thread as a variable, only known by that thread, only known by that thread, as long as the variable that you are defining is not static, then basically every thread has its own stack, okay, and that variable, okay, is known within the thread only. So that's the scope of the variable, the thread only. The third one is the local variable that is defined within a thread, okay, so it's not a global, local within a thread. However, we have used the static with it, In this case, okay, there is only one runtime copy of it, as you know, static variables, right? During runtime, there is only one copy of it. However, we can have multiple threads defining the same variable with the same name as a static. So it can have, this variable can have what? Multiple declarations in the threads by the same name. But at runtime, there is only one copy of it. Okay, don't forget that. One copy of it, which means one thread will change the value of this static variable, it is seen by other threads and so on. Okay? So it's similar to what? To global variable. Of course, a variable is shared as a node there. If it had been referenced by more than one thread, then that variable is shared, for which, again, there are consequences, okay, that we have to take care of. Now we go through the rest of the functions. They're quite easy functions, okay, and I think you can guess how they work and the kind of value they return and so on. One of the functions is called the equal function, pthread underscore equal. That takes two thread IDs and returns back whether they are equal or not, okay? So if it returns back 0, means what? They are not equal, right? If it returns back anything else, then it's equal, usually 1, right? And then also, as we have for the process get PID, for the thread we have what? Pthread self, okay? Pthread underscore self, it returns what? The ID of the thread, okay? Now, using these two together, okay, these two functions usually they are used together, we can demonstrate a very useful application for them, which is this. We might have one main thread, okay, or we call it the master thread, who usually distribute what tasks for threads to do, other threads to do. So we have master-slave relationship, okay? Now that master thread creates tasks and assign it to threads, because the master thread got the ID of the thread, isn't it? Right? So can assign these tasks to threads and putting it where? In a queue. The other threads, who are the working threads, will be looking at the queue, okay, looking at the task, and then they will check, okay? A thread will check whether the task is assigned to it or not. How the checking is done, I need to know the ID of the thread that's supposed to do this task, which is already embedded in the task itself, and compare it to what? To the thread ID. Okay? If they are equal, means this task is assigned to this thread and supposed to dequeue it and work with it. Otherwise, it's assigned for some other thread, then just leave it, right? So this is what? Dispatching tasks, okay, for threads, okay, where these tasks are marked by thread ID, okay? So the thread can know whether the task is for it or not, okay? This is one useful application. We also mentioned something before about the exit, okay? The exit or underscored exit with capital E or that with small e, when you call it in any thread, okay? And we also mentioned that the process is one stream, which means of control, which means one thread. So if you call this there, okay, the exit, it will terminate the whole process. Even if you call it from within any thread, it will terminate that thread and the whole process. So the whole process means what? All the threads also within the process are what? Terminated, okay? To avoid that, we use what? Pthread underscore exit. Pthread underscore exit. So the pthread underscore exit, when it's called within a thread, it terminates only that thread, including the main stream of control, or which is the main thread. If I call pthread underscore exit, it will only terminate that main thread, but not the whole process, okay? The same thing for signal handlers, okay? If you have the process receive or a thread receiving a signal, okay, and we mentioned before that the default action of signal handling involves what? The termination of the process, correct? Termination of the process. So if you send a signal to a thread, okay, and you are not catching that signal, then the default action will be taken. And the default action is what? Terminate the process, not the thread, the process. So the whole process will be terminated, including all of its threads, okay? So we have to, when we want to send signals to threads, we have to catch, and if there is a termination, we will do it for the thread only, right? By calling pthread underscore what? Exit, rather. Okay. Other things, including the pthread underscore cancel, pthread underscore cancel, which can be used to terminate a thread. If you want to terminate a thread, you use what? pthread underscore cancel, which is similar to abort. If you've seen abort, right? In a process, we used to have abort. Abort means terminate a particular what? A thread, and if it's within that process, that particular process. So I can use pthread to terminate another thread. pthread underscore cancel to terminate another thread as well. Okay. The exit, okay, pthread underscore exit, we can also deal with it, okay, or it has a signature that is similar to the exit as well, where the return status can be retrieved. The return status can be retrieved. The exit status can be returned, in other words, right? The exit status can be returned. So we can have the signature of it, which is pthread underscore exit, that returns a pointer to void, right? Pointer to void, because that's what is returned with pthreads. Now, usually what is returned by the pthread exit, you can catch it by another thread, right? Because if I want to know the exit status of a thread, means I'm in another thread, which is most likely to be the main thread, right? So I want to know the status. The status, this one is automatically catched by another, okay, by something, a method that is, or a function. Now I'm started to mix up between, okay, saying function and a method because we're going to start Java soon, right? So pthread underscore join, okay, pthread underscore join. This is a method that is, this is a function that is similar to what? Wait PID. Wait PID. So pthread underscore join is a function that if I call it for a particular thread means I'm going to wait for that thread, okay? So a thread calling pthread underscore join for a particular thread means it's waiting for it to finish, to terminate. To what? To terminate. And it will catch its termination status. And the termination status is caught where in the variable of pointer to what? To rval ptr, which is the return value of the exit status, okay, of the thread, okay? And of course, this kind of waiting for a thread, okay, involves the blocking of the current thread who's waiting, right? However, this thread, when it's blocked, it will stay in the blocking state until it has been what? Either called return, or called the pthread underscore exit, or what? Or being canceled. Being what? Canceled. And in the case a thread being canceled, then the exit status of it will be what? This, which is pthread underscore canceled. Which means the exit status, this one is informative, right? So when I get an exit status, I can compare it with a set of constants to know what was the reason for the termination, right? For the termination. One more thing about pthread underscore join, it's not only similar to wait PID, it is also what? Marking the thread, okay? For whom I called pthread underscore join, okay? It will mark it for releasing of resources once it is terminated. Releasing of resources once it is terminated, which means it calls what? Detach or deattach. Means deattach the resources that the thread was using, okay, at the time of termination, okay? So that's the join. So there is, as we just mentioned, a function called detach, okay? Detach, and then the argument that it takes is a thread ID. If it's called, it means release the resources that were attached with this thread that is given the ID for. Okay, release the resources that it is using. One additional set of functions are related to the cleanup process immediately before the thread is exiting. Okay, immediately before the thread is exiting. Most of the time, I'm not sure whether you have used this before or no, but there is a function, okay, in C called @exit. @exit. I use it with a process, okay, with a process, not with a thread. @exit, okay, is a function that I can make it call other functions to do some kind of cleanup or reinitialization or doing things such as releasing certain resources or changing flags or whatever, okay, before the thread is what? Before the process is exiting. But here I'm not using at exit because that's for a process. So I'll be using another set of functions, that we'll see one of them in a while. Now these functions, I can use more than one cleaning handler. Okay, we call them cleaning handlers because they do the cleaning before the process or before the thread exits, right? I can call more than one handler. So I can call handler 1, 2, and 3, okay? So if I call them in this order, handler 1, 2, and 3, means the way they are going to be executed is handler 3, handler 2, and handler 1. So the calls for these handlers are pushed in the stack, okay? The last one that you called, okay, is actually the first one to be executed. So we have to be very careful about that if we are going to use these. Now, let's compare some of the methods or some of the functions that we have been using with pthreads, okay, to that we used with process, okay? There are some similarities. If I want to create a process, I use fork. However, if I want to create a thread, I use pthread underscore create, right? If I want to exit a thread, underscore exit. If I want to wait for a particular thread, underscore join, which is equivalent for processes for wait PID, right? And if I want to do something at exit time, then I can use pthread underscore cleanup push. And why we use push? Because we know now all of these handlers that we're going to call, we can call this multiple times, each time for a different handler. Be pushed in a stack, and they'll be executed the up first, which means the last first, right? LIFO, right? And there is a function as well, which is pthread underscore self and cancel, which is similar to a port, okay? So that we don't mix up things. I thought this table is, I mean, it's nice really to look at. So now we move to showing you some of the examples, okay, to see some insights of these functions and how do they work. And then we move to another topic, which is basically Java threads, okay? All right. So I have uploaded to the Blackboard 8 programs about pthreads. The aim of these programs are to demonstrate the concept, okay, so that we strengthen our understanding of these functions. Okay, so let me start by we already seen pthread 1, right? Do you remember it? PT1? You've seen this before or no? Okay, so this one, what does it do? A thread, okay, that's created here, okay. The function that has the code of the thread is this, okay, and the function, what does it do? It prints only the PID of the process, okay. And then, what does it do? It returns what? Null. This is the other way of writing null, right? The other way of writing null, okay? So we can write it like this, or you can write it return null, or we can say what? pthread underscore exit, okay? And the cause of any one of these is the termination of the thread only. However, if I use exit, the whole thing is terminated, okay? The whole thing is terminated. Now I'm getting here after creating the thread, then I have sleep 2. Why do I have sleep 2? Why do I have sleep for the main thread? Because I'm not sure. Now after this statement, I have 2 threads, isn't it? Right? The thread that will execute this code and the other thread that will proceed here. Which one of them will execute first? I'm not sure, and for how long. But I want that thread to execute first, okay, and then this one, so I just make sleep, okay? In fact, if I did not make a sleep, here, what will happen? If this one is executing, continue executing after the creation of the other thread, what will happen? It will print that statement and exit, which means that thread will not run at all. Did we demonstrate that before? We shown you how, okay? Let us show you, for example, how really does it work, okay? Did I do anything wrong now? The switch, pthread. Okay? Don't forget that. So I have removed what? I have removed the exit, but did I save it? I did not save it. Okay, so that run for was before saving it. Okay, so now I'm saving it. Okay, I'm running it. Okay, so what do I get? I am the hosting process, and that was printed, the BID. However, the thread did not, okay, have the chance to execute. Why? Because this one ran, print this, exit 0. Exit 0 terminate the whole process, right? The whole process. So I did this to make sure that it's not terminated, because waiting for 2 seconds, the CPU will take some other process to execute, and that would be what? The thread. So we have the thread executing. I am the thread of process, and then after that, the process, okay, or the main thread of the process executing, and so on, right? But however, we said we can, instead of doing this, what we can do, pthread exit. Okay, so now we're going to show you other examples that if we're going to exiting, we use what? Pthread exit. Or let's just, since we already mentioned it there, just put it in here, okay, and show you that it also works. Okay, so pthread, okay. And I put in there null, I'm not in. Okay, let's save it. Okay, so there is no sleep, but however, no exit. There is a pthread exit, right? It works. You can join it as well. So we're going to see much more than that. Okay, while we proceed with the examples. Yes. But usually when we create threads, it's not only that we're going to join them all, because this will become what? Sequential, right? Sequential. Okay. Now what do we have in here? Okay, we have a number. Okay, it says toNumber. This is a global variable, right? Which means we expect it to be shared by all threads, correct? And then I have here in the main, I'm defining an array of type pthread underscore t to hold the IDs of the threads. IDs of the threads. Okay, how many of them? I already defined, which is number of threads to be 5. 5 threads. Okay. Then we go into a loop. In this loop, we are printing that we are creating these threads. Here we are creating the threads. Okay. And what we are passing, we need to pass the name of the method that holds what? The code for the thread, which is here count. So this is the method count, if you notice. Okay? So this is what the thread is supposed to do. It is the body of count. And here I'm catching the ID of the thread, and I'm saving it in the array, which is called what? Threads. Okay? Of type pthread underscore t. Okay? Now, the last argument is what you want to send to the thread. And we said we can only send one argument. And in this case, I'm sending what? I. So the first time I send 0, 1, 2, up to 4. Correct? So this will be, let us say, signaling the task number. Okay? The task number is different than the thread number, isn't it? This task number, you name it, or you can assign it to anything that you want. In this case, sequential. And of course, I can check. And we said before, always when you do system programming, you need to do the error checking code. Okay? So from time to time, we show this code to tell you that. Remember to do it in professional development. But here, we just assume that things are successful. Right. And then I'm having the pthread underscore exit. Pthread underscore exit that will terminate the main string. Our threads are still working, correct? Now, what each one of these 5 threads will do? They are actually going to count to what? to number. And number I'm giving it there what? 20. Okay? So this is what I want the threads to do. I want them to count to 20. But I want them to what? To cooperate counting to 20. So when a thread is working, we'll count, say, up to 5. And then after that, we'll sleep. Another thread will work. We'll count starting from 6. Okay, 6, 7, 8. And then, okay, interrupted, preempted. Another thread will. So the continuation of this count. Don't forget that they are all accessing what? To none. So they know the maximum limit. So that's why here we say while the current counting is less than that, we continue counting. We continue what? Counting. Okay, the current counting, which is the current value that had been counted, if I put it to be atomic variable, then every one of them will have his own count, right? But if I put it static, this counter, then everyone will have access to the same variable, because there is only one copy, one runtime copy of this counter. Even though each one of them executes the code, static integer count equals 0. Multiple declaration, but however, it's what? Always referencing the same variable, right? Okay, so they know. So when one increment count, it affects the others, because it's static, okay? Now, we're having here different versions of this, and we'll show the effect. We'll show what? The effect. So in this case, in this while loop, there will be an increment of count, and then a thread, the one who's active at that time, we don't know which one, is going to print the task ID of it, which already had been passed to the function as arg, right? And we agree that this is a sequential number 0 up to 4, right? So it's going to cast it, always these arguments, you cast it to the actual type of it. Cast it to the actual type of it. We know that I, which we passed it to this, the variable I, is what? Is an integer, so we cast it back to what? To integer, okay? So that's the casting statement, okay? If it's of another type, cast it to that type, okay? Okay, so that's what we're going to print, task ID, which is in here, and then followed by what? The current counting value. The current counting value, which is counter. Then we get this thread to sleep for 1 second. And of course, if it's sleeping 1 second, another thread will execute, right? And we'll continue counting from where this thread stopped, right? Where this thread stopped, right? And so. At the end, each thread will basically finish, okay, after the while loop, if we already reached what? To none. So let's see. Oh, are we going to get in here? Okay, so this is 2. Oh, sorry. So these are the 5 threads created, which are 0, 1, 2, 3, 4. And now, thread 1 is counting 1. And then sleeping. After that, thread 2 counting 2, okay? And then thread 4 counting 4. Look, it's sequentially, right? And then thread 0 counting 5, and then we have thread 1, and then so on, right? So it's not necessarily that they always start in this sequence. In fact, if they are to start really in a sequence, then thread 0 should have started first, but did not, okay? So the counting is correct. They actually have done an excellent job, right? Counting to what? 20. Now let's do some modifications, okay, and what happens? Can you guess or no? For example, if I remove this, what will be the act? What will be the result? Everyone will count to 20, right? So let's see that. As long as we have an understanding of these, okay, I think you can do well, okay, with threading. Did you notice that? The counting to what? To 20, okay? We're not going to wait for them, or shall we? Okay. Each one is counting to 20, each one. Now let's do some other modification, okay? which is basically, so let's get this back here, static. Now, what if I don't have sleep here? What do you think the result will be? Sorry? The first thread that will execute, okay, will be given a slice time to execute, right? Will be given a slice of time to execute. Now, if that time was enough for the thread to execute its code and finish, then it will do the whole job by itself. Okay, and then this thing, what we're doing here is easy, right? It actually is done in a very short amount of time, which is most likely less than the slice time or the quantum time that's given to the thread. So we're expecting this thread to do the counting by itself, right? The very first thread. The others, when they start, they will find num already 20, so they will not do anything, right? Okay, so let's try that. Thread 0. It just happened that thread 0 is the one that started first, counted 20, right? Okay, let's do something else. Okay, so let's leave this. Okay, what about this? Let me have it here, inside the main. What do you think? What will happen? I have saved it, right? Okay. It's not there, right? The threads are using a variable that is not, okay, defined for them. They don't have access to it, right? Okay, so that's one thing. Now let's do this. What do you think? Who's defining this variable? The main thread, right? And it's static. Okay, it is what? Static. So what are we going to get? It exists in the virtual address space, correct? Did we declare it anywhere else? There? We did not. Okay, we did not declare it there. Okay, so the same thing. Okay, so back to, okay, because it was not declared, it's not known for them anyway. We'll do some other kind of stuff later, okay? Or you can even play with the code to see some other things. Now look at this. What do we have? We want to demonstrate how can we send to a thread more than one value, okay? So we said we can do that by putting these values or these arguments in a structure. The structure is what? Heterogeneous type. So I can have different types in it as members, right? Or if they are homogeneous, I can put these types, these variables, if they are of the same type, I can put it in an array. And then pass what? The address of the array, right? Or I can pass a file descriptor or anything you want. So in this case, we are demonstrating how we pass a structure type which has heterogeneous data in it, okay? So what we want to pass is this, okay? bthread underscore data, we call it, the data that we're going to send to the thread, which has integer types, okay, which is the thread ID, actually the task ID, and the sum, okay, as well as a message, which is a string, okay, a string. And then here we are defining what? An array of the structure, of this structure, because we're going to pass to each thread a different structure, okay, a structure with different values. Okay, so we have an array of this structure. Each time we'll pass one member of this array, which has inside it what? A structure that has the values for a particular thread. Okay? Now, the thread is supposed actually to use the values here by printing its ID, okay, the sum and what? A message, okay, a message that it will display. It's gonna actually change sum and print what? The message that was sent to it, okay? The message that we have it in here is basically hello world in different languages, okay? Fine. So, the ID of the threads that we are creating, as in before, okay, we are catching it and we're saving it, okay? This is the, here, okay? For the number of threads that we want to create, okay, and in this case, number of threads, how many are there? You see there, number of threads, 8, okay, 8 at the top, okay? So we're creating 8 threads. Each time a thread is created, we want the thread to add what? A value is added to sum, which is initially 0. That value is the counter of the loop, right? And then this value of sum is sent to whom? To the thread. To send it to the thread, we put it in the structure of that thread. So a structure, okay, I already have an array of it, right? Which is args of 0, args of 1, args of 2, up to 7, correct? These are the members of the array. Every member, for example, here I'm talking about args of 0. So args of 0, it has a member thread ID. Args of 0 has a member sum and a member what? Message. Okay, and what I'm going to save here, this is the ID of the task. This is sum, which is updated by adding the ID of the task to it cumulatively. And this is what? The message that the thread is supposed to print. And we have seen the array before. Okay? So you prepare that, put it in a structure, and then pass the structure. Here, what we're doing, okay, I have the thread ID code in threads array. The function which has the code of the thread, what's supposed to do is print hello, and the argument is this, arg t, okay? I can send it to the what? To the thread, okay? Then the automatic cast is done to void, by the way, if you don't put it there. Now, this main thread will exit. So every thread will receive a different message to print, plus a different value to sum. Now, the thread itself, when it receives what? A structure, correct? So the very first thing to do is to what? Is to have that structure, okay, in here, okay, and do the printing. So what do we have? We have defined these, okay, and then we said what? My args, okay, which are here. Right? My args are what? Thread data, right? They are thread data, okay? And then, this is the structure, okay? We can now, here, do the casting, okay? My args, yes, okay. Okay, so now here we do the casting of thread args, which is, you should be here what? My args, okay. I mix up, okay, sorry. Okay, my args, okay. My args, which is this structure, I want to cast it, okay. I'll cast it to, okay, again, mix up again. خلينا نقول هاي my arg, okay. So this is my args, so I'm casting my arg, okay, to my args, because I know that is going to be like multiple of them, right? Okay, so the argument is my arg, and I'm casting it here to my args. My args is what? Of this one, okay. And then I will extract out of it the ID, okay, that's task ID, the sum, that's sum, and then the message, which is what? The hello message. And I'm going to print that, okay, and then return. Clear? Okay, clear? Structure, cast it to its type, then you access the members of it, print it. Okay, so I'm going to save this. And that's 3, right? 3. So we have created 8 threads, and each one of them is displaying what? The task ID, okay, the message, and the value of sum. Initially it was 0, and then we added 1 to it, it was 1. That's for task 1, okay? And so on. And then the second time you added 2 to 1, so it becomes 3, okay? And then 3 to 3 becomes 6, and so on. Clear? Okay, so this demonstrates how you can pass any number of arguments to what? To a thread. And in this case, we've shown you that with a structure. Okay, I thought I can go Java things, but I don't have time for that, but it's okay. As long as we have understanding of this. Now, this is what? We have data, okay, given in an array, okay, and what we want the thread, okay, a number of threads to work on this data. To work on the data, okay. In fact, I just create one thread. I want to pass the data to it. However, I will do that in different ways. By passing global data, okay, or by passing the data through arguments, okay. And I will see the behavior when I use pthread exit null, or what? Just exit, okay? So I have commented this program for you to try all different possibilities, okay, for passing the data to a thread and see the result, try to explain the result. Explain the result based on your understanding of the functions and how does it work. So what do I have in here? I have an automatic variable. This is called automatic variable, right? Data. And I'm creating a thread that I'm passing data to it. And don't forget, the name of the array is what? Is having an address, right? The name of the array is the address to the first location of the array. So that's why we don't have pointers there, right? Okay. So I'm passing this data to the thread. And the thread is supposed to do what? Okay. It's supposed to find the summation and then display the average as well. So it needs to count. So the thread finds the summation of the data and display the average. The count and sum, okay, are initialized to 0. The data here, okay, I'm having it as values, okay, values. So I'm casting it back to what? Don't forget, you put there, yes, the address of the array, but there is an auto casting to void, right? And then here you have to cast it back. It is what? An array of integers actually is a pointer to integer, right? An array of character is a pointer to character, right? An array of pointer to, so on. So I'll cast it back to integer, okay, values. Now look at this. Values is a pointer to integer, okay? And I can access it as what? By the index. Okay, it will give me the next integer. So it will move 4 bytes forward each time you increment the index, okay, as its consecutive memory. So I can say what? Okay, go into a loop, okay. The termination condition here, I'm not sure about it. Okay, I'm not sure about it because I don't know the size of the array and I'm not passing the size of the array. Did I? And you cannot know the size of the array in C as in Java that way, okay. However, I'm signaling the end of the array by what? -1. So this -1 is not data, okay? If I do want to pass 2 arguments, right? On the other hand, I can pass 2 arguments. I can pass the array and the size of it in a structure, correct? But sometimes we work around things as well. Okay, so I'm saying here, okay, printing the value first, okay, which I don't need here. I was doing lots of testing, okay. So basically, if the value is -1, it means we're done. And in that case, break, go out of the loop. If it's not -1, then add it to sum, correct? And then do what? Continue, okay, by incrementing count, okay? Once you are finished, go out of the loop and print what? What is the sum and what is the average? Do you understand this code? It's very easy code, right? So let's run this code. Start saving it here. It's 4, right? So do I have? Is this correct? Do you believe this? No. What's wrong? What could be wrong? Something went wrong, right? Okay, let's look at the code. The code says, create the thread to do this work and exit. And what? Exit. Correct? What am I sending to this thread? I'm sending the address of an automatic data. Right? And when the mainstream exit, its automatic data are what? Not preserved anymore, right? Subject to change. The thread got a pointer to it. Okay, it's a pointer to memory, correct, it was there. But we cannot guarantee that it will not change. Some of it might change, okay? Some might change. So what happened in this case, this exited before this one what? Finishes, okay? It could be even at the time of the starting of this one, okay? The thread, right? So the mainstream exited before the thread, okay, finishes the job it's supposed to do. So the automatic data, okay, defined by the mainstream is subject to change now, correct? The thread has a pointer to it, but that doesn't mean it's safe. And in fact, the array itself, yes, the array itself here. The array itself is automatic data because it had been defined within a function. That's the definition of it, without static. Without what? Static. Okay, so now I will show you the exact, actually what caused this, okay? So we're printing the values and the sum as well, okay, to see what's happening. Okay, look, when the thread started, what was saved in location 0? That value, right? Which caused the sum to be that. Which means the very first location of the array was not, okay, was the first to be changed by the system, reused by something else, dummy data, right? Okay? So how to overcome this problem? I have to make sure that this main, okay, waits for that to finish, right? Waits for the thread to finish. So I can say what? bthread join wait BID, okay? Wait for what? For the thread which is TID, and we already saved it here, TID, right? And I don't want to catch an exit status. Let's see this now, what's going to happen. And, well, I'm leaving the documentation statement for the printing the sum, okay? Is it correct now? Correct or no? You can see that the data, the very first element of it is what? 10. Okay? And it's correct now. So we know the cause, okay, of why that happened. You can do the rest of the things, such as instead, okay, you can define it static here and see what happens, but without using what? The join, and we already mentioned that, okay? Or you can define it here as what? Global, even though that one finished, okay, it's still available, right? So you can expect the results. So please try these different alternative ways of defining the data, or using the join, and so I hope that you have a good understanding of at least the functions that had been demonstrated to you. Continue looking at the rest of the functions, and next time we'll look at the leftover functions, as well as we're going to start multi-threaded programming with Java, okay, which is much easier. Sorry?
We assign the values to the array. For each index, we have
Yep.
a value for it. And for index 0, it's 10. The value is 10.
Yes.
So we know we can't know the size of the array.
How? When you send an array to a function, how can you know the size of the array?
Size of function doesn't work.
No, the size of function won't work in here. The size of function will return to you, okay, the size of whatever you give to it in bytes. But also, I can have a trick to do something like that and then see, actually, this is an array, okay, of what type, and that type integer, say 4 bytes, the number that's returned divided by 4, and then, but why to do that? I mean, you can just have a very simple thing in there. Or pass the size, okay, pass the size. Sorry? Yes, yes. Yes, keep it, please. But keep it, not throw it, okay, because I might need to maybe get some information from it later.